Okay, welcome back, Science 30s, to our next chapter in chemistry. Today we're moving on to organic chemistry. We often hear the word organic associated with organic foods, organic products, and even organic medicines. And they all have this association with being natural and coming from plants and living things. Now, what the manufacturer of different products means by organic could be different, so it's always good to research what you buy before making an assumption behind that word organic. But the reason why we associate it with plants and nature and things like that is because the term organic means relating to or derived from living matter. And this is where organic chemistry began, studying the chemicals of life. And we could get into chemicals related to food, like glucose and protein and things like that, but also into types of dyes and types of fabrics that we could use for materials and other products. And when we study the chemical makeup of these living things, we find a common chemical linking them all together, and that chemical is carbon. Carbon is good for linking things together because it has 4 lone electrons, or electrons in the outside, that allows it to bond to 4 things. For this example here would be hydrogen. We can see it's sharing those electrons and it can make bonds in 4 places. It's almost like a piece in Lego that has lots of places that can just link together with other pieces, and it causes you to be able to make big chains like this, or even make rings that look like this. And these are examples of organic molecules. So now, with this understanding that life is carbon-based, organic chemistry changed into studying the structure and properties of carbon compounds. This includes all the life stuff that we saw from before, but can also include other non-living things such as plastics that are carbon-based. So now that we understand a little bit about what organic chemistry is, we'll go in a little bit more detail. The chemicals involved are going to be carbon, but then also a lot of hydrogens. It's mostly C's and H's that we're going to be seeing in these organic diagrams. When it's just C and H, these are going to be called hydrocarbons. Kind of makes sense because you have hydrogen and carbon, so it's a hydrocarbon. Now, we will see more than just C's and H's, and other common elements that come up are called heteroatoms. They're commonly found in organic chemistry, and there's a whole list here from nitrogen, oxygen, bromine, a whole bunch of different types like that, which we'll talk about labeling and naming later on. So the next part we want to look at is how to draw these organic molecules, because they could get fairly big and fairly complex. So we want to be able to draw what they're looking like, but also do it as efficiently as possible. So there's 3 types of diagrams that you could see. And I'm just going to start with drawing hydrocarbons to make it simple for the start. So the first is the Lewis diagram. And this is similar to the Lewis dot diagram that you saw previously in the course, but we're going to use lines instead of dots to represent the electrons. So when we have a bond, we'll just have a line. So this is an example of a Lewis diagram. We can see 4 carbons all bonded together, and then the other bonding sites that they have are bonded to H's. We can see where everything is laid out. That's quite a bit to draw, though, if we're going to do that for every single chemical. So we have a condensed structural format that looks like this. So instead of drawing all the lines to the H's, we just put how many H's are bonded there. So we can see 3 H's bonded to a C, bonded to a CH2, bonded to a CH2, which matches the diagram above. That's still quite a bit of writing, though. We still have to put all of the C's and H's, so we're going to go simpler still with what's called a line diagram. And to represent that molecule there, we're actually just going to draw it as that. Now you're probably thinking, how the heck does that represent this chemical? Well, what it's doing is it's taking that idea that all the C's are bonded to H's wherever they have other bonding sites, right? It's 4 C's bonded together, and then all the other places are filled up with hydrogens. So it's just saying, let's forget all the hydrogens and just assume that they're there and draw 4 carbons connected to each other. So without those C's, we have to just know that any end of a line or any corner represents a carbon. Then for the H's, you just know, well, if a carbon is bonded to one other carbon, it's got 3 spots left because it has 4 bonding sites. So there's 3 H's bonded to it. If a carbon's bonded to 2 other carbons, it's got 2 spots left, so it's got 2 H's bonded to it. So we can just make that assumption and we just draw the carbons connected. Now, if it was bonded to something that is not hydrogen, we do have to include that. So if this was bonded to a nitrogen, for example, we would have to put a line and say it's bonded to an N. So I know it seems maybe a bit oversimplified, but it works really well, and we'll take a look at a lot of those diagrams today. Okay, so now that we know what the diagrams are going to look like, we're going to put a name to these organic molecules, and we're going to look today at alkanes. Alkanes means chains of carbon that only have single carbon-to-carbon bonds. If you're looking at double bonds, that'd be alkenes, and triple bonds, alkynes, but we're not going to look at that for this lesson. So just looking at the single bonds, which are called alkanes. Now I'm going to list quite a few steps here, and it's important that we follow all these steps because we want chemists all to name these chemicals the same. There'd be a problem if one chemist called it one thing, another chemist called it another. They wouldn't be able to communicate about these chemicals. So it's important that we follow these rules. So we'll take a look through the list and try and name this chemical below here. The first is to locate the parent chain, which means the longest chain of carbons. Okay, so looking at that diagram, we're trying to find the longest chain of carbons. Remember, an endpoint or a corner represents a carbon. So I could look at this chain of carbons being bonded together and notice there's 1, 2, 3, 4. Okay, that looks like the longest chain, but I could also get rid of that and see that if I follow this path, I get 1, 2, 3, 4. Getting the same number either way, so actually both of these would work. So I'm just going to keep this one highlighted. We can see that on the second last carbon there's a group coming off. The way I labeled it the last time, there was just a group coming off downwards instead of upwards. But we see that the longest chain in a row is 4. Next, for step 2, we are going to label that parent chain. And we're going to use a prefix to indicate how many carbons are in that parent chain. Now this is in your data booklet and it tells you the prefixes here. For 1 is meth, for 2 is eth, for 3 is prop, and 4 is but. Those are kind of weird prefixes to have. The other ones on the other side make more sense with pent for 5, hex for 6, non and octa. These are familiar prefixes probably from math. These first 4 are a little bit weird, but that's what we use for naming organic molecules. So looking at our example, we had 4 there, so we would get the prefix but. And then we have to add the end ane because, again, today we're looking at alkanes. So this would be butane as our parent chain. Next, for number 3, we're going to look for any branches, and we do see that one branch coming off the side. That branch has to get labeled as well, and it's going to use the same prefixes as we saw for labeling the parent chain. So once we found it, that's step 3, and step number 4 is to put the prefix on it. And this is a branch of only one carbon because the line coming off comes to an end point, which represents one other carbon. So that is going to be a 1 carbon, which is meth. Now we don't label this methane because it's not another parent group, so we put a YL and call this a methyl group. If there's 2 carbons, it would be an ethyl group, 3 a propyl group, and so on. Okay, next step, now we're going to number the carbons on the chain, number 1, 2, 3, all the way to 4. Now we want to do this so that the branches, or in this case our methyl group, is on a lowest number. So if I just went 1, 2, 3, 4 like this, I could see the methyl was on the 3rd carbon. But then I just want to try going the other way. So if I remove those and put the numbers going in the other direction, I get the methyl on number 2. You want your branches on the lower numbers, so this would be the correct way to number it. 1, 2, 3, 4 going in that direction. So now it's time to put those pieces together. I have a parent chain of butane, and then I have methyl on the 2nd carbon. So how I'm going to write this is I'm going to write 2 for the carbon it's on, methyl butane, and that'll be the name of that chemical. So it props up here and says that we're going to list the branches in alphabetical order and also include the carbon that they're on. Now the alphabetical order part means that if I had multiple branches, I would put them in alphabetical order. So if I had an ethyl here, ethyl would come before methyl. But in this case, I only have 1 group, so we don't have to worry about alphabetical order there. And the last step here lists what we already have done. We are going to separate the numbers from the letters with a dash. And if we had consecutive numbers, so if there was 2 of these methyl groups, say maybe one was on the 2nd and one was on the 3rd, then I would go 2,3-dimethyl butane here. That's a part I forgot to mention on number 4. If you have more than one of those same groups. So if I had more than one methyl, I would put di for having 2 methyls, tri for having 3 methyls, and so on and so forth. Okay, so I know that's a lot of rules, but we're gonna get lots of practice here putting them into examples. So let's take a look at some simple ones and then get more and more complicated. The first one I'm gonna put up as the Lewis diagram, which is just a straight chain of 4 carbons, what we saw from before. So my first step would be to find the parent chain. The longest list of carbons is right there. I see that there's 4 of them. I don't see any branches in this one, which you will get questions like this where it's just one chain. So all that gets the name of is just butane, and we're all done. Similarly for this one, this is the condensed structure, but it's just a chain of carbons, no branches. So we just find the longest chain. In this case, that would be 6, and we would just call this hexane. Lastly, I'll put up one of the line diagram where we just have a straight line of carbons. I count all of those up in the chain. There's 8, and so that would have the name of octane. Now let's try another condensed structure, but this one has a branch to it, so I need to find the longest chain. So I would maybe first look at this and I would count 1, 2, 3, 4, 5, but then notice that when I went up to there, that took a path where it only went to 1, whereas if I continued on, there could have been a path of 2 there. So I'd have to erase that and look at this as the longest chain, as I can get a chain of 6 here with just a branch of 1 coming off. So I'd start with the parent chain, and that would be hexane. I can see on the chart here, hex would be my group. And then I see that there's a branch of 1, which is methyl. So now I just need to say, okay, what carbon is that methyl on? I could label it this way and have it on the 3, but I should just check the other way to see what it'd be in that case. So I flip it around, and if I label it the other way, I would get it on 4. So I want to go back to that first way and have it on the 3. So methyl is on the 3, and this is a parent chain of hexane. So I would put 3-methyl hexane. There's a methyl on the 3rd carbon, and this is a parent group of hexane. Here's another example. We can see getting a little bit more complicated. This one looks a little all over the place, but our first step to find that parent chain. I look here and I might circle those, think, okay, that looks like the longest chain. I count 1, 2, 3, 4, 5, 6. But if I look at this side over here, I actually could have taken a path of 2, so I should recount that this way, and I count that chain and get 7. So always take a look to see if there's a longer chain that you can find. Okay, next I'm going to label the carbons. I can see I have 2 branches here. I have a branch of 2, that'll be an ethyl, and then a branch of 1, which would be a methyl. But this one I'm going to start by numbering the carbons, so I get those on the lowest numbers. So if I went this way, I can see it on the 4 and the 5, but if I flip it and go the other way, I get it on the 3 and the 4, which are lower numbers. So this is the better way to number it. 1, 2, 3, 4, 5 going in, or 5, 6, 7 going in that direction. Now to name those groups, again, this is 1 carbon coming off. That's a methyl group. This one we can see has 2 coming off it, 2 carbons attached to the parent chain, which makes it an ethyl group. Now this is the first time we've seen an example with 2 different types of groups, and we have to remember they need to go in alphabetical order. So E comes before M, so I need to put my ethyl before the methyl. So the ethyl is on the 4, and the methyl's on the 3. So this is going to be 4-ethyl, 3-methyl heptane. All right, so make sure we're in alphabetical order, and we can see the name there, 4-ethyl, 3-methyl heptane. Which brings us to our last example, this one getting even more complicated. Let's see if we can sort this one out. So first, looking for the parent chain, or the longest one, I could look like this and find it's 1, 2, 3, 4, 5, 6, 7. I could maybe say, well, let's try this other format going like that, and that way I also get to 7. And that's the longest I can get. I could get to 7 either way, so both of those are fine, but I kind of like the one that's more linear, so I'm going to go back to the other parent chain that looks like this. Both of them would be fine though. Okay, so now we're going to be looking at our groups that are going off and numbering the carbons. So we see that we have an ethyl group down there, a group of 2, and then we have 2 methyls in this case. I have one on the top, one on the bottom. So I've noticed all my branches. Now I want to number the carbons so that these are on the lowest numbers possible. So if I number it this way, you'll see that the ethyl's on the 3, the methyls on the 4 and 5. So I have 3, 4, 5. Let's check if I go the other way. If I go the other way, I get 3, 4, 5. So I actually get the same number going both ways. So that seems like it's equal. I'm going in each direction. But what I'm going to do in this case is I think, well, when I'm writing out the name, I'm going to write them in alphabetical order. So that means the ethyl is going to come first. I want to have my lower numbers at the start going to higher numbers at the end. So I actually want to make it so the ethyl's on the smaller number. So I'm going to flip it in the reverse. Okay, it's a very small detail that doesn't pop up too often. Usually you have to put a number one way, but we kind of had a tie for lowest numbers if we numbered each direction. So now we just used alphabetical order. We're going to use the lower numbers at the start of the chemical. So now I have 3-ethyl, 4, 5 is the 2 methyls. Now remember from the steps, it said if you have 2 of the same group, you need to put a prefix including how many there are. So in this case, I have a 4, 5 dimethyl because there's 2 methyls. So I know that's a lot of information. Let's bring it all into a name. I have 3-ethyl, 4, 5 dimethyl heptane is how we name that chemical. Okay, so that concludes our video. I hope that helped you to understand organic chemistry, structures, and naming. Thank you so much for watching this video, and I will see you in the next lesson.